node at the next level of the tree, and likewise till all. And finally, we'll say that we'll have a situation where we'll have either yes or no, and we can take a decision. So instead of actually going formally through the algorithm, so if we take that example, this is how we get the different branchings done, and finally we keep on keep getting a decision where it is to be given access, or if not matching, it will say that it is declined. So this is good. So this is about a binary tree, but actually the height of the tree becomes a little bit larger, and sometimes it may become efficient, as you see from the results. So we have another variant, which is an n-pod tree. What we do here is that instead of a binary decision of this attribute has this value, what we do, we take an attribute and bring out as many branches as there are values for that attribute. We'll see that. And then let us take it here, as we said, that each non-leaf node consists of the following: an attribute, and there are branches for each distinct value of the attribute in the policy, and each leaf node will have a decision which is whether the access is to be allowable. So the input and output are simple. And then here what we do is that how do we choose which attribute at different levels? We choose it based on the entropy, because when the entropy is more, as we know that there will be more disorderliness in the system. So if we can bring things together, then the entropy will be coming down. So what we do is that we choose the entropy, and the standard definition of entropy is used. So if we consider our data, we find that designation has the highest entropy among all the attributes, so that we decide as the root of the n-pod. And from there, what we do is that we see that what are the possible values. So there I had p, y and pn for yes and no. Here for each value of that particular attribute that has been chosen in the node, I find, say, p professor is this rule, p student are these rules, and then the users again which are covered by the rules R1 and R3 we get in this set, and similarly for student. And as you can see that I just had one example, there could be so many different values for each of these attributes. That's why we have an n-pod. So this is how it looks. So we have designation, then professor and student, and then I choose another attribute which is type. So as you can see that here I have chosen type, which is an attribute of objects. Here I have chosen day, which is an attribute of the environment. So depending on which rules are filtered out, you may have different attributes chosen, and which could be from objects or subjects or environment. So finally, as we can see that this would look like this, that from the root as we travel to the next level and next level, finally we have a decision. So what it would mean is that every time we end up in this, I can give access, but if I reach a leaf node and it is not matching, that means that the access will be denied. So what the advantage we get here? We get that, of course, the height of the tree will be much smaller as compared to the binary node. Now the question is that sometimes, as I said, that I could have wildcards also. So handling of the wildcards is a little tricky, because what happens is if there is an n-pod tree, and then say I have a rule like this, okay, R1 which is b equal to b1, so this is an attribute, b is b1, c is c1, and I have some stars, and say this request has come that the values for the user and the objects are b equal to b1, c c2, and d equal to d2. Then say first we check that b equal to b1, so we follow that left branch, b equal to b1, and then c equal to c2. But here you see that c equal to c2, there is no option. So apparently it would mean that the access will be denied. Okay, but you see that there is this b equal to b1 and c equal to star that is there. Okay, so what I have to do is that I have to follow this branch. C equal to star means it's a wildcard. So c equal to c2, that is the request that has come, matches with c equal to star. It is a wildcard. You go here, d. Now what else I have? D equal to d2, but from here there is no d equal to d2. So that would mean that the access would apparently be denied. But then I backtrack, and now you see that there is this rule, b equal to star, c equal to c2, d equal to d2. So b equal to star takes you here, and then we have this d equal to d2 also matches, and c equal to c2 also matches. So if you have these wildcards, things are not that simple. Okay, so you may have to hit the leaf node and sometimes you have to backtrack. So in case of in poultry, that is where there is some performance issues. Okay, so we'll see from the results. So whether you have simple representation of the policies or you allow these wildcards to be there would determine how efficiently your trees would work. So there are some results, but essentially what we have done here is that we have a lot of different sizes of the number of objects like 100, 200, etc. So we have the number of users varying here, and then this is basically the linear search, the first baseline. This is the modified linear search, the second baseline. This is the binary poultry, this is the n-ary poultry, and C tells us what is the number of comparisons, and S tells us what is the speed up with respect to this as the baseline. So we have speed up of 1 here, and as you can see, for all of them, the n-ary poultry has the highest speed up. So for any value you see that n-ary poultry has the highest speed up here, 19 and then 11 and this 1 and 11, 1.64, and this of course is 1. So what we get from this result is that the n-ary poultry actually is the most efficient. Of course, both of these are more efficient than the baselines, but with respect to binary poultry also, n-ary poultry does better. Then if we also vary other parameters, so there are more results, but whatever we do, we notice that the n-ary poultry has much better speed up as compared to the binary poultry, which of course would outperform from the baselines. Okay, so we have very different parameters taking their various combinations. And then again, with variation in the number of attribute values and attributes, so we have done those experiments, and always it is noticed that the n-ary poultry does better than the binary poultry, except the cases where we have some wildcards in the policies. Okay, because for n-ary poultry, what we have to do is that we have to do the backtracking, but for binary poultry it is not like that. With binary poultry, in one go we are checking for the individual values, and as a result what happens is that we don't have to do the backtracking. So binary poultry does better. So here what we have is we do not have the baseline approaches. We have the n poultry and the binary poultry, and with respect to the n poultry, we see that binary poultry has higher speed up when we have some wildcards also in the policy. So things become a little different, and that's why binary poultry has values when we have those types of policies. Otherwise, n-ary poultry or the n poultry does better. So this is the comparison as we see that with increase in policy size and number of attributes and attribute values, etc., that there is not much variation for the binary poultry and n poultry with those. Of course, for the baselines, they vary a lot with the number of policies and number of attribute values. And for the ones with star, as I said, that B poultry outperforms n poultry. So if we conclude what we have done so far and what we have achieved is that we have now a new data structure which two types, basically binary and n-ary poultries, that significantly improve the performance of ABAC systems in comparison to the baseline approaches. And of course, it depends on the type of policy that is supported. And the future directions of this work would be further reduce the number of comparisons if we can use other than the frequency or the entropy, some other metrics to reorder the nodes. Then we might have even a better speed up. Also, what we said is that the frequency and the entropy were all based on the static assignment of the users and objects to the attributes. Okay. So what about the actual access pattern? If the actual access pattern is not following the distribution, this would not work efficiently. Maybe there are only a few users who are students, but they are accessing more often. So you would not like them to be pushed down in your tree. You would rather like to have them higher up in your tree structure. So what we are currently doing is that we are trying to make this data structure more dynamic. So that basically brings us to the end of this discussion, which is about the binary poultry and the n-ary poultry. That is a completely a new idea that we brought in terms of efficient enforcement of. Sure. Just a couple of things. things up. So just quickly, so either we can discuss now about the what, or this is about my other areas. Should I finish it? Oh, quickly, I'll just wrap things up. So I work primarily in access control, as I have discussed today, and also I work in data science field. We have done a lot of work with public sharing on Twitter and fashion recommendation, brand consistency, etc., which are completely orthogonal to the work on access control. And these are some of our publications. So this particular work that I presented was published at ACM SACMAT this year in June in Toronto. And then we also work in other areas where we have different problems on access control, which we have published in IEEE transactions on emerging topics in computing, and ACM TYT, IEEE TIFS, and data science we published in transactions and computation social systems, and very recently on ACM Web Science Conference. So this work was done with my students, Shaptoshi and Ronik, and Mahendra, Arindam, and Bosha, my other graduate students. And I collaborate with Jaideep and Vijay at Rutgers, and in Germany I have collaborations with Professor Riegel and Professor Pradmul in TU Munich and in University of Regensburg. So I would like to thank Alexander von Humboldt Foundation for supporting my stay at TU Munich, where part of the work was carried out, and of course currently I am being supported by Fulbright program. And like I have other collaborators, I always look forward to collaborating with you all. So thank you very much for your attention, and I would definitely love to answer your questions.
Questions? I have a couple of them. Let me start with this.
Sure.
Now, it seems that with this attribute-based structure, tree structure, there will be a lot of application in real world.
Right.
Access to different objects on the internet. You see as I was looking at, I think Ken is here, the Internet of Things,
Right.
where there will be many objects. I think one of this can be well suited. Do you have any thoughts on
Yeah,
that?
yeah. Let me answer it in two different aspects. First thing is that as I was thinking about further extensions of the work of not only the tree structure that we have talked about, but of ABAC itself. So for IoT, first thing what we need is a lightweight access control system, right? So it's important that, so we try to make it lightweight in the sense that how much of efficiency we can bring in terms of enforcement, but also for the representation we have to do something with the IoT sometimes could be resource constrained devices, okay? And these enforcement also has, these algorithms have to run on such power constrained sensors. So there is a definite need for not only improvement in algorithms, but also in their representations and actual evaluations for IoT devices. The other thing that is important is that for IoT devices, typically you would not have like the usual set of users, set of objects known a priori. So ABAC would actually make more sense in IoT devices, okay? But there could be ad hoc requirements for data from other devices. So in that case, what happens is that it's good to say, and that is what I motivated the development of ABAC. So there I can say that node N1 makes an access request to node N2, but N2 will not have a database of all such nodes and decide whether to give access or not. So what I expect is that, that is how I think the research should go, and that is what is my plan also, is that if N1 can prove to N2 that these are my attributes are somehow certified by somebody, then N2, based on those attributes, can give the access. So though N2 does not have a database of all those things, when you are making a request, along with the request also has to prove, like you can give your certificate in case of public key cryptography. So you can prove, N1 can prove to N2 that my attribute is designation attribute value is professor and my department is CS, and that is certified by a trusted third party, then N1 can give the access. So this is the two aspects I think are very important for applications of ABAC in IoT, and that is one of the areas I plan to work on.
Anybody else?
Yeah, please.
So in NPOL tree, for the backtracking part for the wildcards, is the backtracking like done kind of in parallel, or like is it first you hit something bad and then you go back and look?
Yeah, actually good point. So currently what we have is a sequential process. Okay. So what we do is that in any node, say what can happen, I will explain like this. That in a node say designation. Okay. I can have a branch professor, I can have a branch student and a branch star, right? The wildcard. Now the user who has made a request could have the value professor. Okay. Or could have the value say TA. Let us take this example. Now, if it is a professor, then what will happen from that designation? I take the branch professor, go further down, then I do not reach anywhere, come back, then I have to take the star. But if it is a TA, then there is no branch to be taken because there is no branch with TA coming out of the designation, of the node designation, right? So for that type of request, at the very beginning from designation, I will not take professor, I will not take student, I will directly take the star. It will depend on the kind of access request that has come. But having said that, so what we do is that as we hit a node where there is a wildcard, we maintain a list of already those are not yet visited. Okay. So that if I hit blank by searching all the way to the left, as I come back there, what I do is that I take that branch which is there in my not yet visited list with a star. Okay, and then it can go up and up all the way to the root node. But currently we are doing sequentially, so there might be a scope for improvement by doing it.
Yeah, so if for example the professor is in there instead of the TA, so instead of taking just the professor branch, you take both the.
Right, that is a good idea. Yeah, we could take both. Okay. Yeah, but that then we have to have the parallel.
So how does the policy revocation or the rule revocation happens in this?
I'm sorry.
The revocation of policy, like if some rules changed in between.
So good point. So that is what that, as I said, when it is, so this was all about statically deciding it. Now so many things can change, right? That first of all the rules can change in the policy. More rules can be added, right? And as I said, that another aspect of dynamic maintenance is that based on the actual frequency of access, I may have to reorder things, right?
Yeah.
So those are part of the dynamic updating of the tree that we are working on.
Yes,
Because you don't want to reconstruct everything again and again and again, right?
Because
Yeah. So how small changes can be incrementally included in the tree is something that is challenging. We are working on that.
because when you construct it, it might be kind of static. If it's static, then in big organization, the policy and rules.
Yeah, that will be very dynamic. Yeah.
And then the tree will change,
Right.
quite
So
often,
that is
so it might
the
degrade your performance.
true. That is the journal version we are trying to prepare, where the dynamic nature will be in terms of these changes that are happening and also the actual requests that are coming. Yeah. So incremental updating of this one.
Okay, that, let's keep it down the class. We will continue the discussion
Sure.
of the description. Thank you.